All right, these are the notes for 8.4. Start with a bit of a review, so it should look familiar. We write exponential functions as start times growth to the x, which we see right here. Another way they write that is y equals a times b to the x. Note that a in this equation is the y-intercept, or the start, and b is the growth. Exponential graphs can be increasing, which is considered growth, or decreasing, which we call decay. It all depends on what's happening with the number being raised to the exponent. If this growth is more than 1, it is increasing. If this growth is a fraction that is in between 0 and 1, it is a decay or decreasing graph. All right, also to review this one more time, when the change is given to you as a percent, and it is an exponential growth problem, we need to change that percent into a decimal, which here we call the letter R, and then we take that decimal and add it to the 1. Okay, this 1 represents the original population or the original investment, and then that is added. Also, when the change is given to you as a percent and it's a decay problem, say if the item is depreciating 10%, we change that to a decimal, 0.1, and then we subtract from the 1. So, for instance, if something is decaying 15%, then we subtract the 0.15 from 1 and we get a 0.85 growth. And then that'll be raised to the x. So I guess I forgot the exponent here. This should be being raised to the x here, and likewise here. So to reinforce this concept, let's just go through this table quickly. We're given the equation here, and let's discuss the start amount. The initial amount would be 10, because that's our value of a. Now the word rate of change, when we see rate, we know they're talking about percent. So if the growth factor, which is given to us in the equation, is 1.5, you ask yourself, what did we add to the 1? We added a 0.5. Therefore, this rate of change is a positive 50%. And clearly, it is a growth equation. On the next one, we have a start value of 45. The rate of change is 0.75. So you ask yourself, what did we subtract from the 1 to end up with 0.75? We subtracted 0.25, which gives us a rate of change of 25%, but we would say that that's negative because it is decreasing. The factor is the subtracted number, so it's the 0.75, and this is a decay. The next example, of course, the start is 20,000. It is the growth factor is 1/2, so we're losing 1/2 or 50%. So the rate of change would be a minus 50%, and again, it's a decay. And on this last example, there is no number in front of the 3, so we understand that there's a 1 there, so the starting amount is 1. The rate of change, well, the growth factor is 3, so we got to ask ourselves, what did we add to the 1 to get the 3? We added a 2, and then 2 written as a percent is 200%, and this is a growth equation. So hopefully that helps clarify the connection between the rate of change and the growth factor. In this example, we are being asked to find the actual equation in the form of y equals a times b to the x. So we need to find a, the y-intercept, the start, and we need to find b, the growth. But all we are given is a set of xy's that lie on the graph. This 212 point, the xy, lies on the graph, and so does the 596. So since those are both xy's, we're going to plug them in to the y and the x in the equation and write two equations to work with. So in the first one, we have 12 equals a times b squared. And in the second equation, we have 96 equals a times b to the fifth. So this is presenting us with systems of equations. It's two equations and two variables, but typically we've seen these with plus signs. Here we have minus signs, so we need to adjust our algebra a bit. Let's solve. I don't want to solve for one of these b's because then I'm going to be taking the square root. It would be much easier if we solved for one of these a's and then substitute it into the other equation. So to solve for this a, we divide both sides by b squared. So now I have a equals 12 over b squared. So let's take this a and put it into the other equation where the letter a is. So now I'll have 96 equals 12 over b squared and then times b to the fifth, so I will put that in the numerator. Now let's do some simplifying. We have like bases here. We can divide b squared into the b to the fifth, and I'd have 12b to the third. All right, the next step, we would divide both sides by 12. 96 divided by 12 is 8. So I end up with 8 equals b to the third. Take the cube root of both sides, and b is equal to 2. So now I know an x, y, and a b, so I know of these four letters that are in this equation, I know 3 of them. So let's plug in 3 and solve for a. It doesn't matter which x, y you use, so I guess I'll use 12 and 2. So 12 equals, I do not know what a is, times, I'll put the number 2 in for the b, and then it would be squared. So that gives me 2 squared is 4. 4a equals 12. Therefore, a is 3. So now I have my a, I have my b. Don't stop there. Finish the problem by writing the actual equation. Y equals 3 times 2 to the x. Let's look next at an example of a decay problem. Following the start times growth to the x. So writing a function, you can write y or f of x, either way is fine. So f of x equals the start value. If the car originally is worth $25,000, it is losing 5% per year. So we take 1 minus the 0.05, and our factor becomes 0.95. The exponent is the years. So if the number of years is 5, enter this into your calculator. Never, never, ever multiply these two numbers first and then raise it to the exponent. Either enter it like this. Your calculator knows PEMDAS and will do that. Or you can do the 0.95 to the fifth power and then multiply it by 25,000. And then you get a value of the car after 5 years, $19,344.52, if I did that correctly. All right, the last thing we're going to cover in this section is radioactive decay. Write the formula you'd want to write down. The starting weight of the sample times, of course, the growth is half in all half-life problems. What's different is the exponent. The exponent is a fraction, t over h, where t is the time that's going by, and h is the actual half-life of the element. And please note, the time units must be the same for the time period and the half-life. For example, they both have to be in minutes, both have to be in hours, both have to be in days, or you need to make an adjustment. So a quick example. We are asked how much of a 120-gram piece of radioactive isotope is left after 10 minutes if its half-life is 15 minutes. So substituting in the numbers, we have 120 for our starting. It's a half-life problem, so the growth is always going to be a half. And now we have to set up the fraction. The top number is how much time has gone by. Well, we were asked to find after 10 minutes, and this has an active half-life of 15 minutes. So the fraction is 10 over 15. Okay. When you enter that in your calculator, make sure this fraction is up in the exponent. And if you enter that in, I ended up with 75.6 grams are left after 15 minutes.